Okay, what we're going to discuss today is the last topic in the course, non-parametric statistical methods. When the data is generated from a process that's known except for a finite number of unknown parameters, these are constants, the model is called a parametric model. Otherwise, it's called a non-parametric model. Statistical techniques that assume a non-parametric model are called non-parametric. For example, suppose you assume the data comes from a normal distribution with mean mu, standard deviation sigma, both unknown. The data is generated by a process that's known except for those two parameters, mu and sigma. This is a parametric model. Models that don't assume normality or some other distribution with a finite number of parameters are non-parametric. We're going to consider two non-parametric tests, the sign test and Wilcoxon's signed rank test. These are testing the central location of a population. They're alternatives to both the Z test and the T test. The Z test has the test statistic x bar minus mu naught, sigma over root n, so it assumes that the standard deviation sigma is known, or that it can be estimated accurately. The sample size is large enough. The t-test takes into account the extra variability in the statistic when you replace sigma by its estimate. So the non-parametric tests, there's two of them, the sign test and Wilcoxon's signed rank test. These are testing the central location of a single population, and they're alternatives to the Z test and T test, which do that exactly the same, but you assume the data is coming from a bell-shaped curve that is known except for two parameters, mu and sigma. If the data isn't coming from a normal population, the Z test and the T test, they require this assumption, they're no longer valid tests. The probability of a type 1 error might be different than the desired value, 0.05 or 0.01. So the single sample non-parametric tests. The data is not coming from a normal population. It could be coming from any type of shaped distribution. The two tests we're going to look at are the sign test and Wilcoxon's signed rank test. They don't assume the data is coming from a normal population. The sign test. This is probably one of the oldest statistical tests in existence. We want to test whether the median is equal to some value. Like quite often when your data is not normal, the measure of central location is the median, the halfway point. We want to test if the median is equal to some prescribed value, mu naught. It's the alternative if it's not equal to mu naught. You could also have one-sided alternatives. The test statistic, it's the number of observations that exceed mu naught. If mu naught is the median, there's a 50% chance an observation will be above it, 50% chance it'll be below it. That's the definition of the median. So you'd expect about 50% of the observation to be above mu naught. You also expect 50% to be below mu naught. There's the median of a distribution. This is not normal. It's actually bimodal distribution. 50% of the area is above mu naught, 50% is below mu naught. If H naught is true, S, which counts the number of observations out of N that are above mu naught, will have a binomial distribution P equal to 0.5, N equal to the sample size. If the median is not equal to mu naught, suppose mu naught is greater than the median, the chance of being greater than mu naught will be a lot smaller than 0.5. it'll be P, which could be anything from 0.5 down to 0. If the median is greater than mu naught, then the chance of following an observation being above mu naught could be quite higher than 0.5. It'll still have a binomial distribution. So if H naught is true, S is the number of observations that are above the hypothesized center, the hypothesized value of the median. If H naught is true, this will have a binomial distribution, P equal to 0.5, N equal to the sample size. There's the binomial distribution with P equal to 0.5, N equal to 10. The most likely value is 5, but 4 and 6 are fairly likely as well. The critical region. It'll be the regions, the observations in the tail, because that's what you'd expect if you if the median was not equal to mu naught. So I'll locate the critical region in the tails. One choice might be 0 and 1. The other choice, and the upper tail 9 and 10. A chance of falling in that region if it's a binomial with P equal to 0.5 is, you can add up those probabilities, 0.001, 0.0098. They add up to 0.20216. So that means that if you use that as your acceptance of critical region, the chance of making a type 1 error is 2%. I might increase that by adding in the two numbers 2 and 8 into the critical region. When you add those in, the probability of making a type 1 error, alpha, is probability of 0, 1, or 2, or 8, 9, or 10. That works out to be about 10%. An example, suppose we're interested in determining if a new drug is effective in reducing cholesterol. We administer to 10 patients who have high cholesterol and measure the reduction. There is the measurements, the initial measurements, the final measurements, and the reduction. We're wanting to know whether the reduction is coming from a distribution that's located on the positive side, or the null hypothesis that it's not. It's located at 0. There's 2 negative values. 8 positive values are 0. So the null hypothesis, the drug is not affected, the median reduction is 0 or smaller. The alternative is that the drug is effective, the median is greater than 0. The sign test calculates the number of positive observations. That turns out to be 8 if we include 0 as being a positive value. The chance of getting that value, we'll use the p-value approach of getting that value or larger, giving stronger indication of rejecting H naught. 0.0439. This comes from the table for the binomial distribution with P equal to 0.5, N equal to 10. That works out to be 0.0547. That's greater than 0.05, so we can't reject H naught if we use 0.05 as a significance level. The fact that it's close possibly indicates there is evidence, and you might find the evidence if you take a larger sample size. So to carry out the sign test, you compute the number of observations greater than mu naught. Suppose that turns out to be S observed. Compute the p-value. If we're trying to hope that S observed is small, for a one-tail test, it'd be the probability S less than or equal to S observed. Be doubled for a two-tail test. To do that, you'd use the binomial distribution with p equal to half n equal to the sample size, and reject h naught if the p-value is small, less than 0.05 or 0.01. The sign test for large samples. If n is large, the normal distribution approximates the binomial distribution. S will have approximately, it has exactly a binomial distribution with n equal to half, p equal to sample size. If the sample size is large, S has approximately a normal distribution with a mean equal to n times p, n times 1/2. Standard deviation square root n times p times q, square root of n over 2. So we can then just standardize S using the fact that it has a normal distribution and reject it using the normal tables. For a two-tailed test, we reject if Z is greater than Z sub alpha over 2 or less than minus Z sub alpha over 2. You can also use a one-tailed test as well. So confidence limits. Suppose we've got data collected from a sample. Arrange the data in increasing order. So when you put brackets around the subscript, that means it's been arranged in increasing order. X1, X brackets 1 is the smallest value, X brackets 2 is the second smallest, X brackets N is the largest observation. Consider the kth smallest observation, that's xk. And the kth largest observation, that'll be from the top down to k, that's X brackets N minus k plus 1. The probability that the median is between those two values, this will be true if there's at least k observations below the median, and this will be true if there's at least k observations above the median. This is the kth largest. This is the kth smallest. So if at least k observations lie below the median, X brackets k will be below. If at least k observations are above, X brackets N minus k plus 1, that's the kth largest, will be above the median. The probability that the median is between those two values is at least k observations lie below the median and at least k observations lie above the median. The number of observations that are above, the number of observations that are below. This has a binomial distribution with n equals the sample size, p equals a half. So this probability can be calculated for any value of k by calculating binomial probabilities. The probability that the median is between xk and xn minus k plus 1. That's the probability that number of observations above the median is at least k, but smaller than n minus k. That would be p of k plus 1, p of n minus k. These are binomial probabilities with n equal to a half. N equal to the sample size, p equal to a half. So this means that xk to xn minus k plus 1, the kth smallest to the kth largest, is a p times 100% confidence interval for the median, where p is calculated from the binomial probabilities. Summarize. Xk brackets k is the k smallest observation. X brackets n minus k plus 1 is the k largest observation. This is a p times 100% confidence interval for the median, where p is calculated using these binomial probabilities. binomial probabilities with n equal to sample size p equal to half. Suppose n was equal to 10. And we'll use k equal to 2. So adding up from 2 up to 8, you get 0.978. So the second smallest to the second largest, it is a 97.84% confidence interval for the median. Suppose we're interested in determining if a new drug is effective in reducing cholesterol. So it's administered to 10 patients with high cholesterol, and you measure the reduction. Here are the initial measurements of cholesterol, the final measurements for cholesterol, and the reduction. Most of the times the reduction is positive. There's a few times when it's negative or 0. The second smallest to the second largest. The second smallest is 3. The second largest is 15. This is a 97.85% confidence interval for the median. The median is with 97.84% confidence is between those two values. We could have also computed confidence limits for the center of the distribution if it's assumed to be normal, but that requires the assumption of normality. This doesn't require the assumption of normality. Second example, similar example, but we have n equal to 20 patients. They each have high cholesterol. There's the measurements of their initial cholesterol reading and their final cholesterol reading and the reduction. We want to know whether the drug is effective, which would mean that the central value of reduction is positive. You see some values are positive, some values are negative. There's the binomial distribution with n equal to 10, p equal to half. What you do is you take the center value, which is 0.01602. Then you add the two values on either side. Now the center value is 10. Add the ones on either side, 0.160. Keep adding them going on either side until you get something that's close to 95%. That's P6 to P14. That's 95.8%, 6%. So that tells you that the sixth smallest to the sixth largest observation will be a 95.86% confidence interval. There's the data and the reduction arranged in increasing order. The sixth smallest is -1. The sixth largest is 9. So -1 to 9 is a 95.86% confidence interval for the median. Again, for large values, you can use the normal approximation to the binomial. Something that has a binomial distribution with n equal to the sample size, p equal to 1/2 will have a mean, will have approximate normal distribution with a mean of n over 2, a standard deviation square root n over 2. So if I want to find the value of k, so the probability s less than k is equal to 0.025. That's finding the value 2k minus n over square root of n that has an area of 0.025 below it. I know that it has to be minus 1.96. So 2k minus 1 over square root of n is equal to minus 1.96. And from that, we can find the value of k, just solving for k, terms of n. There is a formula for calculating k from n for large values of n. This turned out to be, for 20, 5.6. When I did it exactly here using this, k turned out to be 6. So this works even quite well for n equals 20. For n equal to 40, it'd be 13.8. So you'd go from the 14th smallest observation to the 14th largest observation. For n equal to 100, putting n equal to 100 here, you get k is equal to 40.2. So k is approximately 40. For n equal to 200, it's 86. The next test we're going to consider is an alternative to the sign test. It's called Wilcoxon's signed rank test. It's an alternative to the sign test, a test for central location of a single population. So again, this would be used in place of the Z test and the T test when we assume normality. If we can't assume normality, we can use sign test. We can also use Wilcoxon's signed rank test. The sign test. It simply counts the number of observations. When I want to test if the median is equal to mu naught against either a two-sided alternative or a one-sided alternative, the test statistic I use is the number of observations that exceed mu naught. So I just count the number of observations that are above mu naught and use that to say whether the median is equal to the value of mu naught. If mu naught is the correct median, S will have a binomial distribution with n equal to sample size p equal to 0.5. Now the problem with this is that there might be some observations that are greater than mu naught, but not very much greater than mu naught. There may be other observations that are greater than mu naught and quite a bit greater than mu naught. And the sign test doesn't take that into account. To carry out the sign test, you simply compute the number of observations that exceed mu naught, and then you work out a p-value, a probability of getting a value that extreme or more extreme. If you're using a two-tailed test, you double the one-tailed value. This can be calculated using the binomial distribution or the normal approximation to the binomial when n is large. Reject if the p-value is small, less than 0.05 or 0.01. You can also calculate confidence intervals for the median of the population. The confidence interval, you order the observations from smallest to largest. It's the k smallest to the k largest. That will be a confidence interval for the median. It'll have a certain probability of capturing the median. The probability of capturing the median will be computed from binomial probabilities with n equals sample size, p equal to 1/2. Wilcoxon's sign rank test. This is an alternative to the sign test. Again, we want to test whether the center of the distribution is mu naught. Against the alternative, it's not equal to mu naught, or it could be a one-sided alternative. The sign test, we just compute the number of observations. If I subtract off the observations from mu naught, I count the number of observations that are positive, of these that are positive. Should be close to n over 2 if h naught is true. In Wilcoxon-Seiran case, we rank the differences between the observations in mu naught in terms of their absolute value. The one with the smallest absolute value is given a rank of 1. The one with the largest absolute value, that would be an observation that's greatest away from mu naught, a rank of n. We add up the positive ranks associated with positive values of xi minus mu naught. An alternative, also the sum of the ranks associated with negative values of xi minus mu naught. These are the two statistics. Both of those, if you know one, you know the other. If you add W plus W negative together, you just get all of the ranks. That adds up to n times n plus 1 over 2. And if h naught is true, W plus and W negative should be approximately the same, equal to a half of that, n times n plus 1 over 2. If h naught is not true, W plus will be small, or W negative will be large, or W plus will be large, W negative will be small. So the test statistic is either W plus or W negative. If you know one, you know the other. If the true median is less than mu naught, we're going to expect most of the observations to be below mu naught. So when I subtract off mu naught, most of the observations will have a negative attached to their ranks. W plus will be small. If it's the other way around, most of the differences with mu naught will be positive, and W plus will be large, W negative will be small. You can work out the distribution of W plus and W negative when H naught is true. Use the fact that if H naught is true, there's an equal chance, 1/2, that the sign attached to the rank will be plus and minus. So suppose you had n equal to 4. The ranks would go 1, 2, up to 4. They could all have a negative attached to them. They could have all positive attached to them. These other ones, this is where you have 1 positive, 1 negative, 2 positive, 2 negatives. So we're trying to work out the distribution of W plus and W negative when the null hypothesis is true. If the null hypothesis is true, there's a 50% chance that plus will be attached to a rank, a negative will be attached to a rank. So here they're all negative. W negative would be 10, 1 plus 2 plus 3 plus 4. W plus would be 0. Going through all of this, there we get the distribution of W plus and W negative. W plus will be 0 just for 1 out of the 16 chances. It'll be 1 for just 1 out of the 16 chances, and so on. So this is the distribution of W plus and W negative when n equals 4, and the null hypothesis is true. If I let T be either W plus or W negative, this is the distribution of T. Could be 1/16, it's 0. 1/16, it's 1. So if I add up those probabilities, This is giving you the probability that t is less than or equal to small t. This is the value of t. This is exactly equal to t, 0.12450. This is actually found in the table for Wilcoxon's sign rank test. There's the table for Wilcoxon's sign rank test. Here we have the sample size. Here we have the different values of t. What's in this is the probability of it being less than that value. This is useful for computing p-values. That table only goes up to sample size n equal to 12. For n greater than 12, it's known that t will have approximately a normal distribution with a mean equal to n times n plus 1 over 4. Standard deviation, square root n times n plus 1 times 2n plus 1 over 24. So the probability that t is less than or equal to t can be computed and standardizing it. Here it is the exact values of t being less than or equal to t. This is the values of t. There is the table for a sample size of 12. These are the exact values. These are using the normal approximation, and you can see that they're pretty close. Here's an example. The quantity we are measuring are in patients who have cystic fibrosis, and we're measuring forced vital capacity. This is the volume of air that the person can expel from their lungs in a 6-second period. This is the measurement that's being taken. As time goes on, for cystic fibrosis patients, this decreases with time. If I give the patients a drug, suppose it's a new experimental drug, the question is, will this make the reduction in forced vital capacity smaller? So the design is a matched pair design. The subjects are matched into pairs of patients, usually using their initial forced vital capacity readings. Then one pair is given the new drug, the other pair, a member of the pair is given a placebo. And we measure the forced vital capacity for each member and compute the difference. The placebo should be larger than the one with the drug. If the drug was effective in reducing the deterioration in the ability to expel air. We can either use W plus or W negative. W plus will be the ranks of the observations attached to positive values, values greater than 0. W negative will be the sum of the ranks attached to negative values. There is the reduction in forced vital capacity. These are ones where the patient was given a placebo. This is where they're giving a drug. We're wanting to know whether these values here are smaller than these values. So we'll compute the difference. I've arranged them in an order so that the difference is in order of magnitude, absolute magnitude. If I rank these according to the size of the difference, This is the smallest difference. This is the largest difference in the two scores. Some of these ranks are attached to positive differences, some are attached to negative differences. W plus is the sum of the ranks attached to positive differences, W negative for the small differences, for the ones attached to negative differences. We have to judge whether W plus is large. Equivalently, W plus is 86. Equivalently, W negative is small. We'll use the normal approximation. We have a sample size of 14. We'll use the normal approximation. The mean of both W negative and W plus is n times n plus 1 over 4, 52.5. The standard deviation is square root n times n plus 1 times 2n plus 1 over 24, 15.92. Probability of getting a value this small or even smaller. We standardize W negative and W plus and use the normal approximation. The chance of getting a value that small is 0.0179. So since the p-value is small, we conclude that the drug is effective in reducing deterioration. If you go back to the data, most of the time, the drug measurement was smaller than the placebo measurement. This is saying that that is significant. Maybe we'll stop at this point. To carry out Wilcoxon's sign rank test, you compute either W plus or W negative. Usually you one, which is the smaller of the two. Let T observed be the observed value of T. Compute the p-value. Probability of getting a value that's smaller, even smaller. For n less than 12, you use the table. For n greater than 12, you use the normal approximation to compute those p-values and reject HA, H naught if the p-value is small, less than 0.05 or 0.01. So maybe we'll stop at that point. This afternoon in the lab, I'm going to go through how to do the last computer assignment. Let me just make a comment. I think that non-parametric tests are a little bit more tricky to perform than the parametric tests. I'll give some examples. There's some examples in the assignments. Next day, we'll look at two sample tests. These are alternatives to the two sample t-test, two sample z-test. We'll then go on to non-parametric alternative to the ANOVA F-test. This is where you're testing for the differences in K populations. So at this point, we'll just end the lectures.